Hello, my name is Chris Chu from University Malaysia Sabah. I want to talk to you about how to improve heat removal rate from a natural draft chimney based on our paper entitled Improve Thermal Energy Discharge Rate from a Temperature-Controlled Heating Source in a Natural Draft Chimney. There are two important points from this paper. Cold inflow happens, and it destroys buoyancy in a chimney. If it could be stopped, as shown in the figure on the right by wire mesh, the buoyancy is restored with the net result of enhanced flow, and as you will see in this slideshow, thermal discharge rate as well. So why is this enhancement important? There are different ways to enhance flow or thermal discharge rate. Well, conventionally, to improve a natural draft chimney performance, the height can be increased or the flow area reduced with a cone. This research shows it is possible to build chimneys at manageable heights and at the same time increases its efficiency as long as the cold inflow problem is mitigated. Cold inflow or downdraft or flow reversals are age-old problems with chimneys. It is a secondary flow in the opposite direction to the main upflow at the exit that penetrates into the chimney. It is undesirable because the buoyancy of the hot air or gas inside a natural draft chimney is compromised when it happens. George and Scora were probably the first to systematically study this phenomenon and came out with a penetration formula for air and liquids. My first encounter with cold inflow was during my PhD study. This was the facility used to study plumes and their effect on natural convection of an air-cooled heat exchanger. As can be seen in the photo on the right, smoke flow visualization was carried out and showed that ambient air rushed down into chimney. In 2007, I obtained a grant to study effective plume chimney effect and built this facility on the left. You can see at the pipe inlet here, an anemometer was fitted, which was green in color, to measure the airflow rate through the chimney. My student found that the airflow rate was higher for the chimney fitted with a wire mesh on the top than the arrangement without the wire mesh. This was strange, as one would expect wire mesh to be a flow resistance, hence slowing down the airflow. But the exact opposite occurred. Here we have one set of the results of the chimney research facility at University Malaysia Sabah. There are two series of data. One without wire mesh. That's the blue diamond, and the other with wire mesh installed. That's the brownish red square. And then the enhancement ratio is also plotted, the diamond, the triangle, the green triangle. You can see the enhancement ratio hovers around 1.5 over a range of chimney heights. To better understand the cold inflow phenomenon, experiments were performed on a chimney model in a still ambience. It was 12-inch in diameter at the top exit. The heater was somewhere inside here at two loads, either 750 or 1250 watts. The ambient temperature was room temperature. We shall now watch two videos on smoke flow visualization of the chimney model with and without wire mesh installed. First, without the wire mesh. You can see the smoke goes into the chimney at the center. When there is a wire mesh installed on the top of the chimney, the smoke seems to bounce off the mesh. This means the wire mesh is acting as a block to the cold air inflow. The question now is, so what? We hypothesize that if there is velocity enhancement, then there should be heat discharge enhancement as well for cooling systems, and therefore improve the efficiency of the cooling system. To find out, a CFD analysis will be carried out. The simulation is on a chimney with a simple geometry, a vertical cylinder standing above ground. The dimensions are 100 meters diameter, 200 meters high, similar to a large natural draft cooling tower. To save computing time and memory space, only a slice of the cylinder is simulated. The main points from the simulation results are: if a chimney does not suffer from cold inflow, adding a wire mesh to its exit will give the effect expected, which is a reduction in air velocity due to its resistance. If a chimney suffers from cold inflow, the airflow upward will reduce, since the density difference between the chimney and the ambience is diluted, as can be seen here. By installing a wire mesh across the exit flow area here, it produces a flow resistance which blocks the cold inflow, and the net effect is better density difference, hence more outflow. You can see that this is very uniform temperature in here without dilution from the cold inflow. The heat discharge rate is found by the CFD simulation to also increase. This concurs with the experimental results. In conclusion, CFD has reproduced the effect of blocking cold inflow to a chimney by a flow resistor like wire mesh. There is enhancement both in the airflow rate and the heat discharge rate by blocking the cold inflow for a temperature-controlled heating source. The enhancements are higher as 34%. So what are the implications from the CFD results? The implications are that chimneys can be designed to be free from coal inflow without resorting to increasing its height as the only option. But by blocking it and therefore maintain or achieve higher rate of heat discharge for a temperature-controlled heating source such as a steam condenser or a hot fluid. However, experiments need to be carried out to validate this claim. Thank you for watching this slideshow and hope you enjoyed it.